So this chapter is about canonical correlation analysis, CCA. So in principal component analysis, PCA, we looked for directions in the data that maximize the correlation. In canonical correspondence analysis, CCA, we imagine the situation where we've got a variable x and a variable y. And what we're going to try and do is trying to find variables A transposed x, or a vector A, such that A transposed x and B transposed y are highly correlated. So let's think about that. Let's think about the 1D situation first. Let's suppose you've got data that is just xi, yi, for I equals 1 to n. So data that come in pairs on two different things. So one of the ways we measure association between x and y is via correlation. Correlation measures the degree of association between x and y. It's defined to be the correlation between x and y is defined to be the sample, the covariance between x and y, divided by the square root of the variance of x times the square root of the variance of y. Okay. So I've written it here in terms of the sample covariance matrix, but in general it's defined as the covariance between x and y divided by the square root of the variance of x times the variance of y. That's a correlation. But in terms of the empirical correlation, sxy divided by square root of ssx square root of syy, if we write out what that is, this is going to be the sum of xi minus x bar, yi minus y bar, divided by the sum of xi minus x bar squared times the sum of yi minus y bar squared, all square rooted. Okay, so that's the correlation. It's a scale-free measure. It doesn't matter if I was to multiply x by 10 or y by 10. You can see from this formula it would cancel out. Yeah? So the correlation of alpha x beta y, where alpha and beta are constants, is just the correlation between x and y. So the correlation is a scale-free measure of the linear dependence between x and y. Suppose x and y are vectors. Okay, we're going to try and find a linear combination of the x's and a linear combination of the y's, and we're going to try and maximize the correlation between A transposed x and B transposed y. We're going to call this the canonical correlation between these two data sets, the x data and the y data. So just as we did in PCA, we're going to take our time over defining the first pair, in this case, of canonical variables, and then we'll do it more formally in general once we've seen the idea in the first situation. So let's suppose we've got data xi, which are all data points in Rp, and let's suppose we've got data that comes with it yi, that is data in Rq. Okay. So xi and yi are different information, the different measurements on the same subject. Subject I. Okay. And we're going to join these together in a vector zi. Okay, so we're just going to stack them. Xi, yi. Okay, and we're going to talk about things like the sample mean of the x's, so that's going to be x bar, the sample mean of the y, which is y bar, and the sample mean of the z's, which is z bar, which is just going to be the sample mean of the x's stacked on top in a vector of sample mean of the y's. More important than that though, we're going to need the sample covariance matrix. If we let SZ, let's suppose this is a sample covariance matrix of Z1 to Zn. Well, hopefully you'll be able to see that this is just going to be, in block matrix form, the sample covariance matrix of the x's. In the top corner, the sample covariances of the y's in the bottom corner, and in the off-diagonal terms, it's going to be a sample covariances S, xy, and S, yx. Okay, and in general, of course, Sxx is given by the sum of xi minus x bar, xi minus x bar transposed 1 over n. Similarly for syy, won't write it out. Sxy is going to be 1 over n, the sum of xi minus x bar, yi minus y bar transposed, okay? And syx will be sxy transposed. So as we said, we're going to want to find a linear combination of the x's, A transposed x, and a linear combination of the y's that is, let's call it B transposed y, okay, where A is going to have to be in RP and B is going to have to be in RQ. And we're going to want to choose A and B to maximize the correlation between A transposed x and B transposed y. So we're going to maximize the correlation between A transposed x, B transposed y. If we write this out, this is going to be the A transposed S x y times B divided by A transposed S x A square rooted times B transposed S y B square rooted. So intuitively this makes sense. We're looking for a transform variable from the x's and a transform variable from the y's that are most highly correlated. But unfortunately, the problem is written here is not well defined. We know that the correlation of, let's multiply A transposed x by some constants, let's say gamma A transposed x. Okay, so gamma is just some constant, and delta B transposed y. So gamma and delta here are constants. We know that the correlation is not affected by gamma, by multiplying the variables. Okay? So this is still going to be the same as the correlation between A transposed x and B transposed y. And you can see that from here, right? If we add in a gamma and a delta, and every time an A appears, you're going to get a gamma and a gamma, a delta, a delta. Okay. Well, this is delta squared, square rooted. So delta divided by delta, so they're going to cancel. Similarly here, gamma squared, square rooted, so gamma divided by that, and they're going to cancel. Okay. So if A and B are a solution to the maximization problem, then so is gamma A and delta B for any constants gamma and delta, any positive constants. So instead we change the objective, we change the optimization problem. So instead of using maximizing this objective for A and B unconstrained vectors, we're going to put constraints on the vectors A and B here. So what we're going to do, we're going to change the problem to maximize A transposed S, X, Y, B. And we're going to say subject to A transposed S, X, X, A equals 1 and B transposed S, Y, Y, A, B, sorry, equals 1. So the problem is find A and B that maximize A transposed SXY B subject to A transposed SSX A equals 1 and B transposed SYY B equals 1. If we go back to the problem we had before, so you can see what we're saying is we're going to maximize this term in the numerator here subject to these terms in the denominator being equal to 1. Okay. And what we've done by imposing this constraint here is we've made the solution, made the problem have a unique solution. Okay. Now thankfully there's a link between the solutions to these two problems. So A check and B check are solutions, then gamma A check and delta B check are solutions to the previous problem. So let's go on to this problem, so let's call that star. So they're solutions to the problem before for any gamma and delta bigger than 0. So let's suppose we've got solutions A and B to the first problem we wrote down. Okay, so the unconstrained problem. Can we convert these to a solution to the constrained problem? This one. Okay, so can we convert the solutions to the first problem to be solutions to this problem? The answer is yes, we can. Okay, so suppose A and B are maximize this, then say A check, which is A divided by A transposed S X X A square rooted, and B check, which is B divided by B transposed S Y Y B all square rooted, and A check B check maximize A transposed S X Y B subject to the constraints A transposed S X X A equals 1, well, that's also B transposed S Y Y B. So in other words, if we've got a solution to the unconstrained maximization problem, then we can convert these to a solution to the constrained maximization problem. So that's easy to see. First of all, just check that A check AXX A check. Let's just check that this satisfies the solutions. So this is A divided by A transposed SXX A square rooted times SXX times transposed times A over root A transposed SXX A. So that is indeed equal to 1. And similarly for B, check. So A check and B check satisfy the constraints, then it's clear to see that by the invariance of the correlation, that if A and B maximize the correlation between A transposed X and Y transposed, B transposed Y, then A check and B check also maximize that correlation. Okay, so what we've said is that we started with this unconstrained maximization problem, but we said the solution was not uniquely defined. So we converted it to a constrained maximization problem. And then what we've said is, if we've got the solution to one, we can get the solution to the other, and vice versa.